Our paper is titled Recurrent Halting Chain for Early Multi-Label Classification, and this work was done at Worcester Polytechnic Institute. So the key takeaways from this work are that we define the open problem of early multi-label classification for time series, which is a practical and high-impact setting with many interesting applications. And finally, we propose the very first solution to this new problem of EMC. So what is early classification of time series? Well, the goal of early classification is to train a model that predicts the class of a time series while using as few time steps as possible. So for example, we might have the health records collected over time for a patient, and our patient is associated with the label diabetes, and we want to train a classifier that uses as few time steps as possible and detects that they actually have diabetes. And so the key idea in this setting is that if we're able to get the correct answer early, the actual prediction made by the model has more time to actually be used by the doctor. So the doctor can actually react to the predictions that are made by the classifier, right? So in the real world, lots of problems can best be modeled as multi-label classification problems. So in our example, we might be trying to detect which outcomes or which diseases a patient has out of a list of many diseases or outcomes, and they can have multiple conditions at the same time. So for instance, we might have the same health records collected over time, but now we know that the patient has both diabetes and heart disease. And again, the goal is to train a model that can predict for this time series which classes it is associated with while using as few time steps as possible. So a naive solution to this problem would be simply to take early classifiers and apply them to each label independently, right? So we have one classifier for diabetes, one classifier for heart disease, and they each stop as early as possible to make this classification. But the problem with this method is that since the classifiers are actually separate, they can't leverage the multi-label relationships. So oftentimes in multi-label settings, the labels themselves can be used to infer one another. So for instance, a patient who has diabetes is more likely to have heart disease than a different condition. And so we want to be able to use that information in our classification. And so in this work, we seek one model that is able to learn when to predict each class and leverage the relationships between the labels themselves in order to provide even earlier classifications. And so in summary, a solution to the early multi-label classification problem will predict accurate label sets while using as few time steps per class as possible. Now, this is a hard problem for the following reasons. First off, simply modeling the relationships between the labels themselves is a challenging setting. So this is the multi-label classification setting where we need a model that can both do the standard supervised learning task of mapping the input data to class labels. So in our example, we need a model that can see this shape in the time series and predict that, yes, that patient probably has diabetes. But then also, at the same time, the model needs to be able to incorporate the knowledge of the label-to-label relationships themselves. So it has to have knowledge of its own predictions and understand that oftentimes when a patient has diabetes, that might mean they have heart disease as well. The second challenge is that earliness and accuracy often contradict each other. So consider the two options. So first, maybe we make a prediction for a patient right when they walk in the hospital, right? So we give the doctor as much time as they could ever want to use our prediction. And since we haven't seen any data or very little data, more often than not, we'll make wrong predictions, right? And on the other side, if we wait up until right before a patient's outcome, then chances are we get the prediction correct because we've seen all of the data up to that point, but we haven't given the doctor enough time to actually act on the knowledge. And so the optimal trade-off lies somewhere in between these two options. And the perfect balance depends entirely on the task at hand. The third challenge is that the actual halting locations themselves are unknown. So we assume we don't have access to when the classes should be predicted. So when you're training one of these models to do early classification, the natural question is, if the model stops at a particular time step and predicts that a patient has diabetes, for example, should the model actually be predicted here? Well, in order to train a model, we have to devise a model that doesn't need that information and can still learn early halting points. And in addition, in this specific setting, we have multiple prediction times across different classes, and we have to answer the question of, should diabetes actually be predicted before heart disease? So we need a model that that can handle different orderings of label predictions. So moving on to our proposed method, we call our proposed method the recurrent halting chain. And the recurrent halting chain consists of 3 core components. We have a transition model that models the time series over time along with the predicted labels themselves, one at a time, and then a discriminator network that uses the transition model's representation to predict one class probability per class. And finally, a halting policy network that looks at the transition model's model of the data, it looks at the discriminator network's predictions, and it makes one decision per time step of whether or not the model contains enough information to predict each class. So it makes a decision at every time step for each class, either wait for more data or stop and generate the prediction for that class. So first, the transition model. We model the transition model as a recurrent neural network with long short-term memory update cells. And the input is 3 things: the time series values themselves observed at the current time step, a predicted label indicator vector, which is simply a binary vector with 1 element per possible class prediction, where if an element is 0, it indicates that the associated class has not been predicted yet. And if an element is 1, it means that the associated class has already been predicted. So by feeding this vector into the transition model, we're able to force the transition model to serve as the core component of a classifier chain, which is modeling the conditional dependencies between the labels themselves as they're predicted. And the third input is the previous hidden state of the transition model, because the output at every time step is a hidden state, which is just a vector representation of these 3 components modeled over time. The second component is the discriminator network. The input of the discriminator network is the hidden state from the transition model and the indicator vector. And the key idea is that at any time step, some classes may have already been predicted, and so therefore the discriminator network doesn't get to predict new probabilities for every class. It only gets to predict the probabilities for the previously unpredicted classes. So the output is this class probability prediction. The way we do this is rather intuitive, and it can be extended and made more complicated according to the task. But in our experiments, we use one affine layer to transform the hidden state into a vector, which has this number of one element per possible class prediction. And then we use the sigmoid function to project it in a probabilistic space, where the higher the probability, the more likely the time series is associated with a particular class. So then, using the indicator vector, we use the indicator vector as a gating function to make sure that at any given time step, we're not computing new probabilities for classes that have already been predicted. And the third component is the halting policy network. And so the halting policy network is the core of the earliness in the model. It takes in the hidden state from the transition model, along with the class probabilities predicted by the discriminator network. And its output is 1 halting decision per unpredicted label. And so it treats the early classification problem as a Markov decision process, where at every time step, we have to take an action. Either we wait for more data, or we halt and predict. And so what this means is, if the halting, and we do this for every class, and so if the halting policy network chooses to halt for one class, we just grab the element from the corresponding element from the class probabilities vector that's been predicted by the discriminator network, and we return that to the user at the current time step. And if it chooses to wait, we simply wait for that class and until the next time step, when the halting policy network is applied again. And so this problem is solvable using reinforcement learning, which we'll talk about during the optimization. So putting all of these 3 components together, at every time step, we are predicting whether or not to add the current predictions from the discriminator network to a growing predicted label set. So at some point after reading the time series, either all classes have been stopped and predicted, either positively or negatively, or we run out of time series. And at that point, we just use the discriminator network's final predictions for the unpredicted classes. So how do we actually optimize the recurrent halting chain? Well, the transition model and the discriminator can be optimized together using binary cross entropy. And since the halting policy network treats early classification as a Markov decision process, we can use reinforcement learning to optimize its weights. In this case, we use the policy gradient method reinforce. And Finally, we add one last loss term that allows for tunability between the two goals of earliness and accuracy. So the key idea is the user has access to this one hyperparameter where as the hyperparameter grows, the focus on earliness grows. And so a high lambda forces the model to make early predictions. And the model the whole while is still learning to balance these two contradictory goals. So now how do we evaluate? Well, we focus our experiments around human activity recognition tasks where subjects carry their smartphone around with them while doing day-to-day activities, and then they go back and they annotate which activities they did at different times. And so the core task is, given a window of smartphone sensor data, we want to predict what the person was doing during that window, or which actions they took during that window, while using as few time steps as possible. We do this using two different data sets. So the first is the human activity recognition data set, commonly found in the UCI machine learning repository. The first one is a scripted data set, and so it's an easier problem where the label relationships themselves are actually very strong because the actions are taken in a fixed order. So they might be laying down, and then they're sitting, and then they're walking, and that order doesn't change. The second data set is much harder because it's collected in the wild. Subjects would carry their smartphone around with them while they perform day-to-day activities, and then they would go back and say what were they actually doing at different time steps throughout the day. And so this means that the label orders themselves are not fixed at all. The label relationships between themselves are actually realistic and complicated, and the relationships between the input sensor data and the labels themselves is much more challenging. So since no other methods can be directly applied to the early multi-label classification setting, we have to augment state-of-the-art methods for both early classification and multi-label classification to solve this problem. So first, we augment two early classifiers with binary decomposition to make them multi-label classifiers. And binary decomposition is simply training one separate classifier per label, or per possible label prediction, and aggregating the results. The first early classifier is the eLSTM, which is threshold-based earliness, where at every time step, the model predicts one probability per class. And then as soon as the predicted probability surpasses some threshold, it simply stops, and we use the prediction at that time. The second one is most closely related to our method, and it is a reinforcement learning-based halting method, which is in line with much of the recent work on early classification. And so it also treats early classification as a Markov decision process, choosing at every time step either wait or halt. And as soon as the method chooses to halt, it stops and the prediction is used. But the key weakness in this setting is that, of course, it doesn't handle multi-label prediction. It doesn't model the multiple labels at the same time, and therefore it can't handle multiple sources of reward at the same time. The second group is the multi-label classification algorithms, which we augment to become early classifiers by using a fixed halting strategy, which is fairly common in practice, where we simply choose a time step when the algorithm should stop and make a prediction. So each class is predicted all at the same time, and that time when it's going to be predicted is fixed, and it's preset. So the first of the multi-label classifiers is just simply the LSTM using binary decomposition. So we train one classifier per possible class, but they all stop at the same early time step. And so we can choose that early time step when we want them to predict. And then the second is an order-free classifier chain, which again, we apply it at, we run the model, we run an LSTM encoder up to a certain time step. And then at that time step, we apply an order-free classifier chain to make all of the label predictions at that early time step. So our experimental setup is we train all of the models to halt at the same time steps, and then we evaluate the predictions made for each class according to two different groups of metrics. So the first evaluates the ranking of the soft predictions, or the class probabilities that might come out of the model directly, and we do this using AUC metrics. And then second is the evaluating the hard thresholded predictions, which says we actually have to make a decision from the class probabilities of which class does the model think the time series is associated with, and we evaluate these predictions using Hamming loss and micro and macro F1. So we make a few key takeaways from both of these data sets. The first is that the classifier chain method beats the binary decomposition method, both with fixed halting strategies. So this indicates that on these data sets, using a multi-label classifier is actually beneficial. So it's better than splitting the task into different classifiers. The second observation is that the adaptive halting methods, which actually find a unique halting time step per instance, are better than the fixed halting strategies because they're more adaptive and they allow for, and they're much more flexible. And then finally, our proposed method, the recurrent halting chain, because it contains both of those other two features, makes more accurate label assignments earlier than state-of-the-art alternatives. And then finally, since we have this extra parameter of lambda, which controls the earliness, we demonstrate that it is actually tunable between the earliness and accuracy, which is a favorable trait in line with much of the recent work in early classification. So as lambda increases, predictions are made earlier and earlier. And so we can see that when lambda equals 0, the predictions are as high as they ever will be. And then as lambda increases, the prediction accuracy, or really the micro F1 and the instance AUC, go down smoothly. The trends look very similar for the other metrics, and we have those results as well. And so in conclusion, in this paper, we have proposed the recurrent halting chain, which is the very first early multi-label classifier. The problem itself of early multi-label classification is widely applicable, and there are lots of very cool directions that can stem from this work. Our proposed solution is very easily tunable between earliness and accuracy, and we've got more experiments to demonstrate that. And in our experiments, we found that our proposed method makes more accurate label assignments while using far fewer time steps than the state-of-the-art alternatives. So thank you very much for watching. I hope you have lots of questions, and feel free to either use whatever chat system they set up for KDD, or send me an email at twhartbigson@wpi.edu. I'd like to thank my 3 collaborators on this paper, along with our institution, Worcester Polytechnic Institute, and this work was funded by the NSF and the US Department of Education. So thank you again.